This video will describe the sun and its structure. Another video will talk about energy source from the sun. But the sun, of course, is very important in our solar system, supplying the gravitational effects that keep the planets in orbit, supplying energy to the planets and their various interactions that will be covered in another video as well. But some things you might want to think about for the sun. If we kind of take it for granted, the sun rises, the sun sets, we've got this warmth during the day. What would happen on Earth if the sun would stop shining? How many more years will the sun continue to provide this level of energy? And is it possible in the future the sun might provide too much energy for the Earth? So those questions will not all be answered in this video. In fact, none of them in this video, but look for another video. And I'll be recording another one shortly about the energy source of the sun. A few things about the sun you're possibly aware of. The sun, of course, is much larger than the Earth. The Earth looks big because we're close to it. But in terms of the physical dimensions, you could put about 110 Earths across the diameter of the sun. So this is not the volume, but just the diameter is 109 times larger. In terms of volume, we can put in about 1.3 million Earths inside the sun. 1.3 million Earths would fit inside the volume of the sun. And the mass, the sun is 330,000 times more massive than the Earth. 330,000 times more massive than the Earth. So truly, the Earth is insignificant compared to the sun. Let's learn a little bit more about it. In terms of the size, in terms of other objects as well, we have the solar system here, Jupiter and the Earth. There is a white dwarf star that's a companion of Sirius. We have the moon's orbit around the Earth, and then we have the sun. So the sun is larger than the moon's orbit around the Earth. And again, a remarkable object. The mass compared to the planets, so the blue is the sun's mass. This little wedge at the top has a couple of colors that you can see, Jupiter and Saturn. But even those massive gas giant planets are insignificant compared to the mass of the sun. How do we know what the sun is made of? We've not had any missions that dip down a little cup into the solar atmosphere and return that to the Earth. Instead, we analyze the light from the sun. So this is a spectrum of the sun, and from red down to blue, showing us absorption lines. These dark lines in here, and some are whiter, are created by atoms in the atmosphere of the sun, in the upper atmosphere of the sun. And we presume, and computer models would agree, we presume that the composition of the sun is very similar to its atmosphere. But the sun is basically hydrogen, helium, and then various elements are effective at creating these absorption lines. And a measurement then of the composition, if we take a look at the chart here, hydrogen and helium comprise most of the sun and the universe, really. Here's a little logarithmic scale, so you have to get used to this. This is not a common linear scale, but the numbers are decreasing very rapidly as we go down here. But we have the light elements being most abundant. There is a little peak for iron. There's a good reason for that in the way that stars process nuclear fuel and create elements. And then on out to uranium is low here, lead a little higher, as there are decay products of these radioactive isotopes that are stable when they become lead. But little chart here, most important, hydrogen, helium dominate the abundance. The lighter elements are more abundant than the heavy elements. How about the structure of the sun? The sun can be labeled into different regions. The portion where the visible light comes from is called the photosphere. the photosphere here. And there are some atmospheric layers above the photosphere, the chromosphere and the corona, but the bulk of the light comes from the photosphere. This is a region where the temperature is good to create the visible light from red to blue, and it does create beyond the visible range, but primarily energy from the photosphere is coming to us in the visible range of wavelengths. And the density of the material here is good enough to have a lot of atoms emitting light, but it's not too dense above here to absorb that light. So this photosphere, and this is a gas region. You should never look at the sun, but if you look at pictures, you'll see a fairly sharp cutoff between the photosphere and darkness in most photographs above the photosphere. Okay, below the photosphere, we have a zone of convection where hot material is rising up to the surface and falling back down, the convection zone. Deeper down, there's a radiation zone where the energy is being carried by light and bouncing, even more bounces than what's shown in the diagram here, but the energy is slowly going out from the core to the surface. A couple 100,000 years can be involved for the energy produced at the core, for that lump of energy, that amount of energy, to reach the photosphere and be radiated. The radiation zone, where light carries the energy, and then where the temperature is changing more rapidly, convection takes place and carries the energy. This hot material rises, delivers energy to the photosphere where that energy is radiated away. That cools down the material and it sinks. In the core, we have where the energy is being produced. Very high densities here, about 14 times the density of lead, but it's not a solid and not a liquid. It's still a gas because of the high temperatures. Temperature about 16 million on the Kelvin scale, and it doesn't really matter what temperature you use, scale you use at that point, about 16 million. So that would be our structure of the sun. Sunspots on the surface here, we'll talk about those in another video. But a massive object generating an abundant amount of energy, and we'll talk in a future video about the lifetime of the sun. So that's where this video is going to end, and we'll stop our video here.